Hey, what's up, everybody? Welcome to the Robotic live stream. Today, we're going to be talking about the Rock R3 V2 versus the DJI L2 LiDAR system. And we have our Andrew Ginkgo going to be presenting to us. But first, I want to say a few remarks about Robotic, and thank you all for being here today with us. As you all know, we've been around for about 4 years making innovations in the 3D space, originally coming out with our R1A LiDAR system, which quickly went to the R2A, and then we had the R360, the R3 Pro V2, and our latest, the R3 V2. This is the most affordable system that we've come out with to date. It competes with the DJI L2, which we're going to talk about today. And also, we have our Rock Cloud software, which allows you to visualize, process, and analyze 3D data, Rock photogrammetry, Rock Slam, Rock mobile mapping, and today I'm going to show you some things about Rock Gaussian splatting, which is going to be pretty cool. Now, just so you know, we have three big categories of products. We have our hardware. So you can buy our hardware, get 3D models, beautiful, highly accurate 3D data. We have our software, the Rock Cloud. You can actually use this with any hardware, including DJI L2, which we're going to show today. So everything you're going to see today is going to be shown through the Rock Cloud software. And then we have our Rock Pro services. And the Pro services is your outsourced GIS team that can take your 3D data and get you those CAD deliverables. So you can actually engage with us on one, two, or all three. So it's really up to you. But regardless, we're here to get your 3D needs met. And every day we're innovating and trying to create new products and new accurate methods of capturing data to create new training modules to teach you how to do this effectively and really just get your back when it comes to your 3D data needs. Oh, also, we have the whole rock base network that we worked with GeoNet. It's a whole distributed GPS network to do RTK corrections and pull down your Rhinex data in post to PPK processing. Now, before we get into the DJI L2 data sets, I wanted to show you something really quick, a little sneak peek about something that we've been working on. So, Patrick, can you pop that open? So this right here is a little sneak peek of something we've been working on. So this is what we call a Gaussian splat, and this is a 3D environment made only with photos. So look at that, guys. So this is a new 3D technique called Gaussian splatting, and I'm just going to let the image speak for itself. We created a method that you can actually create a 3D environment and walk around. And we created obstructions, obstacles, and the ability to just tie together mini splats in a web viewer. And you can actually view this on your phone as well. So this is coming soon to a browser and a phone near you. So stay tuned for that. And this is just the next evolution of what we're working on here at Rock. But today, I think we want to talk about the DJI L2 versus the Rock's R3 V2 LiDAR. Now, before we jump into Andrew, a couple things about the R3 V2. We released it at $16,000. So at this price point, you're able to get in with a highly accurate system. It can mount to the DJI M350 drone, the DJI M300 drone, and we also have our universal mount, which allows you to mount it to any other drone that can carry it, the FreeFly Astro, the Inspired Flight IF800. These systems are great systems to carry that payload. And you're going to get that highly accurate, about 2 centimeters accurate at a recommended AGL flying height of those 3D point clouds. You can pull curbs off of it. You can engage with our Rock Pro services team to turn that 3D point cloud into a CAD model and then bring that right into Trimble Business Center or Virtual Surveyor or Civil 3D and work on the deliverables that we provide to you to finish your Alta surveys or et cetera, topographic surveys, whatever you're doing. So with that being said, also the R3 V2, you can do slams and you can put it on a car. So when you're looking at an investment, so if you're comparing the DJI L2 to the R3 V2, the investment is just a couple, like $1,000 more. But now you can do slam, you can go inside of buildings, in caves. You're going to be able to do some of these Gaussian splattings in the future. But all of that is going to come with that package. And that's why we believe it's actually a much better offering than the L2 because of that versatility, because of your capital allocation and your ability to leverage that tool in many different scenarios. So, you know, when you think about spending that much money, because it is a lot of money, guys, like this is not cheap. And you really want to be able to use it everywhere. But anyways, that being said, why don't we jump in today and talk about what does that R3 V2 compare to the DJI L2? So Andrew, would you want to jump in and take our guest away and show them a little bit about how that works?
Sure. Thank you, Harrison, for that introduction. Hello, everyone, and welcome to today's webinar. I will say it's been a dream of mine to have an intro that included the Mutts Cuts van. So happy to make that dream come a reality. As I mentioned, my name is Andrew Jenko, and I'm excited to guide you through a detailed comparison of two LiDAR units, the Robotic R3V2 and the DJI L2. Both of these units are high quality tools for collecting and analyzing LiDAR data. And today we'll dive into their similarities, differences, and use cases. If you have any questions during the presentation, please feel free to ask them via the chat box, and we'll do our best to answer them during the session. Now, as Harrison mentioned, before we dive into the webinar, please know that Robotic, we sell and support both units. If you determine the DJI L2 aligns with your specific needs, we are here to help you succeed with that unit as well, and you will have access to the full suite of support methods from Robotic. So let's start by discussing data collection. This is a critical aspect of any LiDAR workflow, and there are some key differences between these two units. First, let's look at drone compatibility. The DJI L2 LiDAR unit is designed specifically for use with DJI's M300 and M350 drones. The ROC R3V2, on the other hand, offers greater flexibility. It can be flown with any drone that supports the 1.26 kilogram payload, giving you more options for hardware integration or meeting contractual obligations such as NDAA or Blue compliance. Next is going to be collection methods. The L2 supports airborne data collection only, which means it must be flown from a drone. In contrast, the R3V2 supports airborne collection, SLAM collection, and mobile collection, making it a more versatile tool for collection settings. And the ROC Cloud allows users to merge LiDAR datasets collected using airborne, SLAM, and mobile data collected in overlapping areas. It also has a 360-degree scanner for capturing more complex features out of straight nadir, such as facades. For mission planning and flight parameters, the DJI L2 relies exclusively on the DJI Pilot 2 application. The R3V2 gives you the flexibility to use either DJI Pilot 2 or ROC Pilot, which can better align with your preferred workflow. ROC Pilot also allows you to see your LiDAR data being collected in near real time. Finally, when it comes to data capture setups, the L2 requires RTK corrections during data collection, adding a layer of complexity. The R3V2, however, allows you to use a PPK processing workflow, eliminating the need for RTK during data collection. Now let's move into data processing and how these two units differ in their workflows. For the DJI L2, data processing is done using DJI Terra, which comes with a significant limitation. Its license is locked to a single computer. This means the dataset can only be processed from that specific machine. For the ROC R3V2, processing is done using ROC Desktop. Its floating license allows you to activate it on one computer, return it, and then activate it on another. This flexibility is particularly valuable for teams collaborating across multiple machines. It also allows you to field check data without internet connection if you activate the license prior to leaving your office. Another key difference is ROC Cloud integration. After processing in ROC Desktop, R3V2 LiDAR data can be seamlessly and directly uploaded to the ROC Cloud. This upload process of your LiDAR, trajectory, photo, and orthophoto data also compresses the files to reduce storage space requirements, making it easier to manage large projects and go directly to point cloud visualization and editing. Then you can share your project directly with teammates and clients. If you generate your LAZ file in DJI Terra, you will need to create a new project in ROC Cloud and manually upload all associated files to get started with your point cloud visualization and editing. Next, we want to compare some real-world data sets collected with these sensors so you can appreciate their specific qualities. We will be examining all of the data sets in RockCloud, our proprietary LiDAR data visualizer, analyzing, and sharing tool. Let's begin by looking at data sets captured with the DJI L2. So we'll start by analyzing an optimized data set and zoom into specific areas to showcase the alignment, accuracy, and density of the DJI L2 dataset. As I mentioned, this data was optimized when processed using DJI Terra. The first example we're going to look at is looking at a height profile, and this is going to be on the flat street in the survey area. So within RockCloud, if you click on Show 2D Profile, a 2D profile along the measurement path will be rendered. What you can do is then zoom in along that profile and inspect. Now, as we're looking at this data set, a key feature I want to point out is you are looking at the data being displayed in GPS time. And by being able to display in GPS time allows you to do high quality checks of your data to ensure accuracy. And so what we have on this flat surface is we have the green points and the blue points overlapping for nearby flight lines. And so what we can do to verify accuracy is zoom in, change our orientation, and see how much offset, if any, is present. And so as we do that, we can now look directly into this overlapping area. We can see that the green and blue points from different times collected in the same area have a very strong overlap. And you have a GPS time slider that allows you to focus in on these specific areas of overlap, manually change what data is visible to help you with this QA/QC process. Visually, what we can see here is really high quality alignment in the overlapping points. And actually what we want to do is go to another measurement within RockCloud where we can measure the height difference between points in this overlapping area. Now, it's going to be really difficult to see this height measurement, and I kept it in there by design. And the main reason is that because the difference measured between our overlapping points for the different time is about 0.5 centimeter. So it's very difficult to see it, but that does show the accuracy for this data set. So right here on a flat surface, overlapping areas, 0.5 centimeter accuracy. That is great. We want to see that. Now, another way that we can check accuracy on specific features in this data set is to look at our curbs. Curbs can be great features because what they're going to allow us to do, again, using GPS time, is we can see how well the characteristic of the curb face is maintained and how accurate that is. And again, within RockCloud, you are able to do 3D rendering, change your orientation and visualization, and adjust the GPS time slider to see how well the curb data aligns for different times in the same area. And with this, what we can see, again, is some really good alignment along this curb. We have very minimal noise, which is a great thing that we would want to see. And actually now, if we look at another height measurement for this curb, what we can see is that we have about a 14.5 centimeter change from the top to the base of the curb. And I want you to keep in mind the slope percentage that we see, which is calculated again in RockCloud, of about 76%. So just remember that number. So what we're seeing here from this optimized data set is it's definitely high accuracy. There is not a lot of noise, and we're seeing repeatable features within these flat surfaces. So that's great to see with this data set. But now what we want to do is we want to take a look at what DJI L2 data is going to look like if you don't apply any level of optimization for the data. And so, you know, the only difference when we process this was that optimization applied in DJI Terra. So for an optimized data set, algorithms are going to attempt to minimize the offsets in overlapping flight lines, which can lead to improving the overall accuracy and reducing the noise. So now let's see what happens when no optimization is applied. And we're going to be looking at essentially the same measurements in the same area for this data set. And so now, again, if we look at that 2D profile along the road surface and we allow it to render and we zoom in, what we can do now is when you hover over those points within the profile, you will see the corresponding X, Y, and Z value be displayed for the points that you're looking at over to the left of your profile. And we have that here. Now, visually, sometimes there, you can say, well, kind of look like the last one. There's not that much. But now we can actually get in, use those Z values, and see how much noise would actually be present. And so in this case, it's significantly higher. And again, to help drive this point home, if we close down that 2D profile and look at it from the same angle and the same view that we already looked at the other one, visually, we can see there is much more noise being present in this non-optimized data set. Again, we can use our GPS time slider to see how that variation in the data collected from the same area at 2 different flight passes, the noise that's present and how that's affecting our data. Now, again, what we want to do is we've seen that there's increased noise, which for a non-optimized data set, that isn't too surprising. We would expect to see that. What we want to see is how much noise is actually present. And so similarly to the first data set, which is optimized, we have a height measurement. And now for that height measurement, what you can see is closer to 5.5 centimeters of offset between the base and the top of the points in that area for the point cloud. So this is kind of begging the question of, we do see, this is where we see increased noise and therefore kind of reduced accuracy. So our question is, all right, with the optimization, how did it reduce that noise? Was it using the top of the point cloud, the base of the point cloud? Do the algorithms focus on the midpoint or a standard deviation? There can be some processing algorithms can leave you with a lot of questions as to how the resultant data set got there. And also the other aspect with a optimized data set versus a non-optimized data set is going to be maintaining the shape of key characteristics and specific features. So as we already looked at a curb, we're now going to go to a second curb for the L2 data set. Now, before we get into any of the measurements, what we want to do again is just change that view so we're looking at it from the side. We can get an understanding of the noise and we can use our GPS time slider. So the red points that you're seeing right here, those are going to be your later time points. And then as we pull the slider back, we can see the earlier time points. We can get an idea of that overlap in this area. Now, what we can see is certainly that there is increased noise. And we are to expect that. This data set is not optimized. But then, without optimizing the data set, what are we seeing as far as the curb and the angle of and the shape of that curb? And so, again, we're looking at 14.5 centimeters worth of change in the curb. However, this time we see a slope percentage of about 83%. So what this is telling us is that with DJI Terra processing the L2 data, when we optimize our data, we are definitely going to see a reduction in noise. We are going to see improved accuracy, but we're going to lose the shape and character of specific features. Whereas with a non-optimized data set, we're going to see increased noise, reduced accuracy, but it's more likely that the character of the faces of curbs and things like that will be maintained. And so this gets us into the question of what's the main goal? Do we want to, especially on an engineering or civil design project, do we want to maintain those faces of features like curbs at the cost of reduced accuracy? Or do we want to have improved accuracy but lose the fidelity and shape of our curbs? Now, this might be, some might call this foreshadowing. I only wish there was an option where you could maintain the visualization and the shape of curbs while also reducing noise and improving the accuracy. And so with that, we're going to go to our R3 V2 data set, which was collected in this area as well. Again, we're looking at everything in GPS time, and we're going to go through the data set the same way we've been going through all the other ones. We're going to look at that profile, the 2D profile along the flat road in the center of the area. We're going to look, we'll see what the 2D profile shows once it renders. Again, it can always take some time based upon it, and you do have the ability to zoom in to both the 3D profile that we're seeing, as you can see right here, as well as the actual height profile of your measurement. Hover over points on the height profile, see how the Z value ranges, and get in there and get an understanding of your data. So again, if we close down our height profile and just focus on the 3D point cloud, we look at our GPS time slider and we're going to pull it back so we can see how well our later and earlier time data for this flat surface overlap. So as we have that light green, light blue, and we bring in the darker greens, we're going to see a pretty good alignment. Now, again, we're not seeing a lot of noise. This would indicate high accuracy, but we want to get a true measurement in there to really understand it. So just like we did with the other data sets, we have a height measurement, and that height measurement is going to give us an idea of the overall accuracy. And again, this height measurement might be difficult to see for height number 1. And what we can see is that we have a height of about 2 centimeters. So that is getting us to our survey grade accuracy of 3 centimeters or less, or 1/10 of a foot, if that's what you're looking at. So what we're seeing already with the R3 V2 is high accuracy point cloud, a reduction in noise. Now, as I said earlier, we want to look at the curve. And I think I should have, I might have glanced over this, but I maybe alluded it to foreshadowing. There has been no optimization. You can see that in the title of this data set. Rock Desktop, when processing your R3 V2 data, does allow you to apply no optimization, low, medium, or high, so that you can reduce noise. But again, what we want is to have reduced noise, high accuracy, while maintaining fidelity. And so that's where you don't want optimization to be present. And so if we look at our curve now, which we know that was our comparison for the non-optimized versus optimized L2, we can look at the shape. We can use our GPS time slider again to focus on how well those points align in the overlapping area. So we have our blues and our greens and our yellows. And what we can see is really good alignment, minimal noise along this curve. So that makes us, indicate, again, high accuracy, low noise. But now we come to our height measurement. And in this case, again, we have our 14.5 centimeter drop, but what we want to focus on is that slope percentage. So in this case, that slope percentage is 89%. So now what we're seeing is much more of the maintaining the vertical face of that curve. So what we found is that for our L2 data, in order to get high accuracy and reduce noise along our curve, we need to apply an optimization. And what it's going to do, it's going to flatten out slightly the shape of that vertical face. We're going to be in the high 70s for our angles, as opposed to much closer to that 90-degree angle. With the L2, once we go in there and don't optimize the data, we're getting closer to the actual angle of the curve, but at the loss of accuracy and the increase in noise. So, and then as I alluded to earlier, with our R3 V2 data set, what we found is that we're getting a point cloud with 2 centimeter or less accuracy. We are seeing much less noise, and we are seeing a great maintenance. We are maintaining the true shape of features on site that you would care for in your engineering or design projects without having to apply any optimization of the data. So that's an understanding of flat areas. And I know what everyone's might be thinking at this point is, LiDAR in flat areas is great. It's going to have wonderful accuracy. But the real reason we love LiDAR is vegetation penetration. We want to make sure that if we have vegetation on site, we are able to see through that vegetation and get down to our surfaces. So now we want to focus on our point density, and more specifically, the nominal ground point density within polygon measurements. So what we're going to do is we're going to look at some nominal ground point density measurement. We're going to look at some area measurements that are generated within Rock Cloud. We're going to start with a smaller one again along the flat surface. And within Rock Cloud, for your area measurement, you are able to click on and generate your, you're able to calculate the nominal ground point density for your area of interest. And this is going to do is that's going to give us the density of bare earth returns that can be used to generate a DTM. The higher that number it is, the more confidence we can have in our DTM. So this is just a small 20 square meter, maybe 25 square meter area in the middle of the road. Again, flat surface, but we just want to use it as a reference to show off the tool. And what we're seeing is this is our L2 non-optimized data set, and we see a nominal ground point density, or NGDP, of around 5.6 points per square meter, with around 3,500 points for the nominal point density. So that is, those are high numbers. We would have confidence in our ground surface. Now, again, we want to move to an area in this non-optimized data set. We want to get to a vegetated area, and we're going to focus on area 2. This is going to take a little bit longer to calculate that nominal ground point density and point density, just because it's larger. This is about 440 square meters, but we do want to get a great, that understanding of how vegetation penetration is working within this system. So again, within Rock Cloud, for any area or polygon measurement that you generate, you will have the option to click on the calculation for this. You will be able to get your point density and the ground point density. So while that is calculating, what we are going to do is just kind of say, what we want to think about is, in this case, we do have some highly vegetated area that we're making a measurement. So would we expect our ground point density to increase or decrease for this area? Now, because of the coverage of the vegetation, I'm thinking we should see a decrease. But the question is, how much of a decrease are we going to see with the DJI L2 sensor? And then again, we're going to repeat this with the Rock R3 V2 sensor. So it looks like it's still calculating. Again, this takes some time. I promise it went a bit quicker. I'm going to go ahead and give the number while it calculates, and it should show up. As I've said before, Scout's honor, you can trust me. But for this area, we got about 4.7 points for the nominal ground point density per square meter, and a similar value of over, I think it was still in that 3,800 points for the point density. So, this does give us an idea that with the nominal ground point density, it is going to decrease when we have more vegetation, but we're still seeing a good amount of vegetation penetration with the DJI L2 sensor for this area. It looks like it's still calculating. Again, I promise I'm not putting my thumb on the scale with some of these numbers. If we have to, these data sets will probably be made available after the fact as demo data sets so you can come in and make your own measurements. But now what we want to do again is we're going to duplicate this with the R3 V2 dataset. So as we transition over to that, again, we don't have any optimization that's taken place. And we're going to start with that smaller area. It's just our 20 some odd square meters in the middle of the road. And we are going to go in, we're going to click to calculate that. So again, what we can see here is we have a nominal ground point density of roughly 5.8 points per square meter. And we've got a nominal point density of about 440, it looks like. So while we are seeing a decrease in the point density with the R3 V2, which fewer returns that isn't much of a surprise. We are still seeing that we can get great ground classification based upon the point cloud using the algorithms within Rock Cloud. So now we're going to move over to our larger vegetated area to see what our ground point density looks like for that specific area where we have the heavy vegetation. Again, you will need to click on it to start the calculation. Depending upon the size, it will take some time. And while that's calculating, I do want to take a moment just to tout the value and benefit of Rock Pro services. So through Rock Pro services, you can get this classification of tall vegetation, low vegetation, high vegetation, noise, ground surface, buildings, structures, so on and so forth. So by doing that, that's where we're able to get these calculations for the ground point density. We've done that on both of these data sets. And let's do a check to see how that calculation is coming along right now for our non-optimized data set. Might have to kick it off again. But again, a larger area, it's going to take a bit longer, but this is where the benefits of having Rock Surveyor ordered for your data sets and allowing our pro services to help you with those GIS deliverables, your classification, generating contours, determining the surface is going to be extremely beneficial. So just as a reminder, what we saw is that we had roughly, it was about in the 5 point, excuse me, where was it? Sorry, I think I may have misspoken, but for our L2 data set, we were looking at about sorry, for our L2 data set, the non-optimized, we had a value of about 3.6 points, 3.6 points per square meter for our nominal ground point classification. And we're going to see what comes back with this R3 V2 data set. I do want to wait for it to be calculated. And then, so we'll go through. We're waiting for it. My notes are showing me, I'm pretty sure the number was going to be about 2.9 points per square meter for the nominal ground point density for this. So we are seeing a lower value for the R3 V2. However, what we want to keep in mind is that there it is, 2.9. So we can see that that is lower than what we saw with the DJI L2. However, if we take the time and we go up and turn on the surface for this area, we can see that even with a lower NGDP for this area, we can get in there and we can see a high quality surface that has been determined from this data set. And that surface, we can also get contours. So right here, if we zoom out, we can see things like the smaller creek bed, the roadway where we did some of our flat measurements. And so again, even with just a smaller amount of nominal ground point density with the R3 V2 data set, we're seeing a really high quality surface and contours being generated from that data set. And again, no optimization has been completed. So this is a great representation of the ground surface. And as you can see within Rock Cloud, there's the ability to, with your contours, you can change the contour type, whether it's low, medium, or high. Right now we have it set to high, so you can really get in and see those very small changes in the landscape. And you can also change any kind of smoothing that you might want to display for the contours. I don't think we want to put it on our roughest, especially with the high, just because I'm worried about things rendering and crashing. Don't want to have egg on my face. So right now, I hope we just want to bring it all back and tie it together. So what we saw for this, for our 3 data sets, where we looked at R3 non-optimized, and then the 2 DJI L2 and optimized and a non-optimized. For our accuracy, we can achieve that survey grade 3 centimeter or less accuracy with non-optimized R3V2 LiDAR data and optimized L2 data. When we don't optimize the L2 data, we're not reaching that survey grade accuracy threshold of 3 centimeters or less. Now, with the noise, we see higher amounts of noise with the non-optimized L2 data, not surprising. And with our L2 optimized and our non-optimized R3V2 data, we do see a great reduction in that noise. Now, when it comes to the maintenance, or excuse me, maintaining the features like curbs, we see that the non-optimized R3V2 is going to do a great job of maintaining that shape, whereas the L2 optimized is going to cause those the shapes of those features to be smoothed out. Now, with the L2 non-optimized, we are able to better maintain the shape of those features, but we do have the added noise and it's not survey grade. So we also see vegetation penetration for our R3 non-optimized and our L2 non-optimized. So we are able to get a good amount of nominal ground point density for these data sets, and then we can use that to generate quality surface models, contours, and classification of the data. Now, what we want to move into is a couple more of the R3 V2 datasets that we've collected and we want to use as examples. So we're going to move into an area that we like to call the 56 Ave, or as some people will call it, it's Taco Bell, because that was the main thing we saw and where we set up for our dataset. So this is our next R3 V2 dataset. Again, this dataset was processed in Rock Desktop without any optimization, because we really want to be able to check out how well we maintained the shape of our features like curves. We're looking at everything in GPS time. So one thing I also want to point out, now that we're looking at just straight R3 V2 data, we're not focused so much on DJI L2 data, is you now have the ability to go into the layers, zoom out to the full coverage of your data set, and you can see your trajectory and your photos that were also captured and were uploaded to Rock Cloud. Remember, this is going to be a seamless upload. So when you go in and you have the ability to look at things in 2D like we are now, you can see the location of your photos, your trajectory, and your ortho photo that was also generated. Again, this is part of the whole suite that you get with a R3 V2 LiDAR unit. And now you can go in there, turn on the photos, and if you click on the unique photo location, you are going to bring up what we call Rock Inspect. And so when you click on that, you're going to render your photo, and you will have the ability to zoom in and pan around to specific areas of that photo. So now you can use this. I mean, imagine you can really see where your parking lines are, where you have curbs, where you have sewer grates, where you might have sloped ramps for ADA compliance. And so this is something you can go in, you can look at it both individual photos or your ortho photos. You could even go in if someone left you a note that said, my GCP location is at the X on a specific utility cover, you can find that in the area. Now we don't have a, so right there, if someone presented you a photo or gave you field notes to show where they made their GCP measurement on that utility cover right there that we see in the center of the photo, you have the ability with Rock Inspect to find that and use it to help you align your data. So this is some of the functionality that you're going to get within Rock Cloud after you've processed and uploaded your data. And so now what we're going to do, one of the first things that I always like to do when I get a LiDAR data set, I'm going to come in, I'm going to just focus on my data in GPS time. I can turn my photos off, I can turn off the measurements, and I'm going to look for a curb where I have overlapping data. And so right now we're going to go to our, we've named it Curb Compare 1. And again, I'm sorry if you're getting bored with curbs, but these are just absolutely fantastic features to get in there and see what kind of noise, what kind of data repeatability, and what kind of vertical shape maintenance you have on your curves. And so again, once we're zoomed into that area, we can use the GPS time slider feature to see the overlap. And so what we have there, we can do the orange to the red, see that red come in, and we're looking at great overlap. And we can also come in there, we can make our measurements. We didn't do the height measurement in this one specifically for the curb. I've just spent enough time out at this site to tell you they are vertical curbs. We're getting a vertical measurement on them. You can see that visually. What we can also do, again, we can look at the flat surfaces of the road and use our GPS time slider to, again, verify for that accuracy. So we do have a height profile in here, just like you would have, we saw earlier. So if we click on that, it's going to take us to our measurement. We can see the area of the measurement outlined in yellow. We can bring up our 2D profile, allow it to render. We're zooming in. We're seeing what type of Z ranges we have along that measurement. So we can either do that in the 2D profile. We can go over to the measurement and again, use our GPS time slider. I don't want to, I don't want you to think LiDAR unit is nothing but curbs, roads, and GPS time sliders, but this is one of the best ways to really get into the gritty details of your data quality. And if I ever look at a data set for a customer or a data set that I've flown, this is kind of the first thing that I look at. I also know the first thing Harrison looks at when he checks my data sets is something like this. So it's a great functionality within Rock Cloud to see it. But again, we're seeing great overlap. We're seeing a reduction in noise. We're seeing a maintenance of that vertical curb face at this, urban environment where we have, this would be standard of an engineering project. You're worried about your curbs and gutters. You're worried about ADA compliance. You're focused on getting planimetrics in there. And so we're seeing the R3 V2 really shine in this type of environment. Again, for this data set, we generated contours and a surface. So we'll bring that up and show it to you. Now, not surprisingly, in an area like this, that surface isn't going to show much variation just because there's not a lot going on there topographic wise. But if we do bring in our contours, we would need to turn them to high. And this is where you can see really those small changes. This is going to be really helpful if you are working on a parking lot and you want to find those bird baths. What's an area where we might get water pooling? So we did this for pro services for this area. You can also, see where water might collect on the edge of buildings, if that could be a problem. So great work here with the contours and the surface done by the pro services team. Again, if you were to load up your data set to Rock Cloud, the pro services team would be just that, an extension of your team to get you the surfaces and contours that you need to meet your project goals and delivery dates. Now, again, people might be thinking, it's LiDAR. I'm tired of looking at curbs. I'm tired of looking at flat surfaces. Give me vegetation penetration. So we'll transition to another data set flown with the Rock R3 V2 LiDAR unit. This is going to be a creek bed environment. And so what we want to do here is really highlight the vegetation penetration capability of our Rock R3 V2 LiDAR unit in an area with vegetation and with a pretty complex stream bed. And so typically when we think of some kind of stream bed, we might think, broad banks in case of flooding. Well, no. In this case, we have a really steep and incised channel with pretty vertical wall, close to vertical walls on the side. And so what we want to do, again, we're going to look at some measurements we created. I'm going to make this quick, but I want everyone to be able to see it. We have our first height profile to show the data quality on one of the flatter areas where we have a pedestrian path in an area of overlap in GPS time. Again, I don't want you to think it's just looking at flat surfaces, but this does, again, it highlights that we're getting great repeatability and high accuracy in our LiDAR data. But now what I want to do is go to our second height profile measurement, which is going to be longer and cut through our vegetation and into our creek bed. So as we bring up that profile, it's going to take a moment to render. But what you can see is once it does render, and another thing I want to point out, and you're getting a great example of this, that profile is not set in place. You can move it around. You can expand its height. You can expand its width. That was more, excuse me, that was for the 2D viewer that in the height profile. We may need to do a reload. But what that profile is going to show once it's rendered, and so you have the ability to, there we go. We might need to just do a quick dynamic zoom to the data. There we go. It's coming up. And so what you can see is we've got the tops of the trees, we've got all the vegetation, but also if you see that part right here that we're zooming into, this is our creek bed. And that's what we really care about. You could imagine if you're trying to use traditional survey methods to get in there and understand the shape and characteristic of a creek bed or some sort of drainage system, and you've got vegetation over it, that traditional method is going to take multiple people. It's going to take multiple hours or days on site to get that. This data set was flown in about 15 minutes. I was on site for about an hour, was able to survey in GCPs, all the while explaining to my 8-year-old son what I actually do for a living. Not surprisingly, when it wasn't the drone taking off or landing, he was a bit bored, but I do think this is pretty awesome to come in here and see that actual penetration through the vegetation to get a great understanding of the true characteristic and shape of this stream bed. And again, as I promised you, it's not all just looking at curves. We're looking at a different type of vertical face here or near vertical face, but this is kind of a different environment as opposed to the more standard urban environment that we were looking at previously. So great. Yeah, now we're really getting in to see with our data, and it might actually be better to show everything in the elevation profile as opposed to GPS time. So now you can really see these blue values being that creek bed, and you have an elevation range that you can change to really highlight and bring out those smaller changes. And now look at it. We can see how many points are actually getting through to that creek bed. We're gonna, again, we used Rock Pro services to generate a surface for this. And before we turn the surface on, we're gonna look at one last measurement, and that's gonna be a polygon measurement so we can get that calculation of our ground point density before we get in there. So if you remember, we had roughly, I think it was 2.9 to 3.6 in our vegetation area. And so now we're taking that time, we've calculated here, and this for this vegetated area with that large tree that you see, we're getting close to 9 points per square meter for our nominal ground point density with the R3V2 unit. So we can have great confidence in the DTM and the contours that our Rock Pro services team took the time to generate. So when we turn that on, first we're going to turn on the surface, let that render. And this is going to give you a really great understanding of the true characteristic and shape of that creek bed and also the nearby drainage that's running parallel to it. So right now, kind of as we hold our view, we're looking straight into that creek bed. And so here you can see that true nature of the creek bed. And we can see the near vertical face on one side and incision, which is great. And now if we kind of zoom out, also, just because not everything is a meandering channel, you can see the irrigation ditch that's running perpendicular to it right there. This also could be used for a number of engineering questions or projects. And also now we can turn on our contours and again, see what we have in there as far as the complexity of the site. And so what we want to make sure of is with the contours, once they're on, we have the ability to expand it. You can change that smoothing level. You can change the contour level. And so if we kind of just zoom out to the full extent, we don't really have to go in there, make much changes in our orientation. What we're seeing is a high quality set of contours and surface for this area along that creek bed with the irrigation channel, doing it all with the vegetation running right over and alongside the top of our creek bed. So this is really highlighting the great capabilities and the high accuracy of the R3V2 in that environment where it's not all flat surfaces and there's plenty of vegetation present. It's complex. You can get all that using the R3V2. You can get these final surfaces and contours with taking advantage of Rock Surveyor to get all this generated for you. And so now we're going to just do a quick recap of our, we're going to move on to our SLAM data set. I just checked the time and we'll do a recap at the end, but I want to get to a data set that we definitely can't make a comparison to with the L2. That's going to be our R3V2 SLAM data set. And so an environment like this is Union Station in Denver, is a great candidate for SLAM collection because this rock LiDAR unit, and we just want to hold this steady for a moment to let everyone get an understanding of the environment that we're working in. So this is a large train station. You have a lot of people present, you have a lot of infrastructure present, and you have buildings that are built up vertically along the sides of your train station. And so this is just not a great area for drone survey capturing. You could have safety concerns. You might have altitude restrictions, and you just might have legal restrictions from flying there. And so you could also have GNSS issues where you're flying in that kind of corridor with all the buildings. You're going to get poor GNSS readings. So how do you go in there and survey it? Well, with the R3V2 unit, you take the camera off, you can put it on our SLAM dock, you can attach an Insta360 camera, and it's as simple as walking around and collecting your LiDAR data. So now what you can see here, those blue dots, those are going to be the photospheres that we've generated, similar to your airborne data set. If you click on one of the points, you can see that 360-degree image that's been rendered, and you can look at it. And so in this case, this is a path over the train station where you can see those buildings that are over a dozen stories tall nearby. You can see all the people you might not want to be flying over. You can see the infrastructure getting over there to the train station on the other side of the walking path. So this is a great environment for SLAM. And now what we want to do is we want to show our point cloud. And again, because we collected this with that Insta360 camera, we can colorize our point cloud. We're just not looking at GPS time. We're just not looking at intensity or elevation. We get a colorized point cloud. And we're going to go to our area that we've called SLAM Area 1. This is just we're going to focus on what we can see in here. So if we zoom into that area and we change our orientation, this should give you an idea of what we're seeing on a standard kind of train platform at a train station. What we can see is we've got those train tracks off to the sides. We have the yellow line on the train platform that is going to be serving as that sort of safety barrier that everyone knows don't stand on when the train's coming. But you can also see the actual individual parts of the train track. You can see the infrastructure that's present with the overhangs to keep people dry when it's raining or snowing. You can see a ticket kiosk or the timetable that's going to be visible. This is all from just collecting a walking data set with the V2 SLAM dock for the R3 unit, colorizing it and generating it. You can see the walking path that was used, so we can see a great overlap through this area. And then again, we're going to look at another area to highlight the quality of this data set, but also the great functionality of SLAM. So if we go to this SLAM Area 2, we're going to change our orientation so we're looking in the opposite direction. So what's really helpful here is that we can see off to our left side, we have all the detail of the structure of the train station. And if we look off to our right side, we can start to see the vertical face of the buildings that are just on the other side. This is the actual train station over there of Union Train Station. That's where you'd go in. You could get your Amtrak tickets. As with all train stations, there's a bar there. You can catch a seat, get warm. But also what I want you to see off in the distance is that walking path that's above the ground level and your train platform. So for this SLAM collection, we were able to walk fully along the train platform path, get full coverage of the area, get full coverage of the vertical face of the train station, but then also continue that path up and over onto the walking path over the train tracks. And we can see all of that in here, all able to process it, bring it all together, colorize it, And the same functionality that you're going to have that we already went into with Rock Cloud as far as making measurements, looking at the vertical features, the angles that are maintained, we can still see that with this SLAM data set. And again, there's no way with the DJI L2 you can collect that type of data set. In an area like this, if you had the L2, you are forced to probably not fly or not get high quality data. You're not going to get penetration through the overhangs. And you're probably also going to get a lot of people saying you can't do this. So this shows the great versatility of the R3 V2 LiDAR unit. And that just isn't offered with the L2. Now, we don't have a mobile data set, but similar to the SLAM dock, you have the mobile dock for the R3 V2. You can attach that to a vehicle, drive through your site, and produce a point cloud like this. So now with that, we're going to start wrapping things up because we've had your attention for about 55 minutes. And so we're just going to move on to the conclusions. So in conclusion, while there are notable differences between the R3 V2 and the DJI L2 LiDAR units in terms of collection, processing, and analysis, both can be high quality LiDAR tools to meet your company needs for data collection goals. We do think that the data sets that we've presented with the measurements inform you that the R3 V2 unit is the superior offering when you consider the data quality, versatility, collection methods, ability to merge datasets from multiple collection methods, Rock's outstanding support, and Rock's focus on development to continue to take your LiDAR surveying into the future. We focused on the R3 V2 unit for this presentation. We focused on the R3 V2 unit, for this presentation because it's our newest offering, and you may be wondering how the R3 Pro V2 fits into this. The R3 Pro is still our highest selling LiDAR unit with double the lasers and double the data collection opportunities as the R3 V2, but both are excellent tools, and the best way to decide which one will fit your needs is to determine your specific data collection goals and project goals. The Rock team is here to discuss that with you at any time. So we thank you for joining today's webinar and hope you found the comparison between the two LiDAR units helpful in understanding the differences and strengths between the two units. Now, if we have any questions, I can take them on. I think a lot has been getting handled in the chats. So, all right. So Darko had a question. What's the AGL flight height for both the LiDAR units? Those are going to be in the 45 to 50 meter range for the comparison ones with the R3 V2 and the DJI L2. For the two data sets where we didn't have comparison, that East 56 Ave and Van Bibber, that was going to be 40 to 45 meters AGL. We have a question about pricing. The best way to determine the specific pricing for the unit or bundle that you are interested in is going to be reaching out to sales@rockrobotic.com. As Harrison mentioned, the starting point for the R3 V2 is going to be that $16,000 entry point. But again, as you build out bundles, if you want to do the SLAM dock or the mobile dock, that will change the pricing. There's a question about, do you have photos of this site too? This site, I need you to be more specific. Do you mean like on ground site of the photos, or do you just mean the photos that we generated using that are kind of part of the bundle? So with that, I'll kind of answer my own question without knowing how quickly the response will come in from Ryan. So we specifically don't have, oh, Harrison might take it.
Well, I jumped on with you, Andrew.
Okay.
Actually, did you, Ryan, which one were you talking about? Were you talking about the SLAM data set or the aerial data set? So both of them have photos, and then you can upload the 360 photos for the SLAM, and you can also upload just the regular photos from our 26 megapixel camera from the R3 V2. So both of them are uploaded, and you can, the
Yeah, so the site that we did for vegetation penetration along the creek, we uploaded the photos as part of processing. We generated the ortho photo for it. So that would all be available through Rock Cloud. And again, you have the ability to choose to upload based upon your trajectory. Yeah, and so you can upload the ortho photo or not. So yes, we have all that.
Well, Andrew, good job, man. Thanks for leading the presentation today and getting all those questions answered. It was really exciting to see the team here at Rock kind of go out and test these tools. That's one of the things that I've been really proud of our team is that we actually get our hands on all the equipment. Everyone goes out, we test it. We're running new calibrations all the time as well, make improving the product. And then whenever we do have more advances, we deploy that to the fleet of systems that you own. So you'll see your Rock desktop will update over time, and all these little things that are happening is to get that last little, quarter of a centimeter, half a centimeter more accurate on your hardware. And then over time, I think the other cool thing was that people that bought the R3 Pro original, we created an update called the V2, and we gave people a path to upgrade their hardware into that new V2 realm. So one of the things is we're trying to, through software, is to continuously improve the performance of these equipment. And that's been something we've been kind of always trying to do. And sometimes there's a hard reset saying, oh, we need a different piece of hardware. That's when we release a new product line. But we've been pretty set in on the R3 product line and improving that for the past couple of years. And I think we're still very committed to continuing the improvement of that. A couple other big improvements that happened is on our pricing. I saw that question come up, and I think that's a great question because we've been working on the back end to reduce the pricing on our side. So your desktop software, along with the Rock Cloud, now we like bundle all this together, and we reduce the price. So on that uh, entry level R3 V2, that comes with your desktop software and the cloud. So we're trying to make it such that because what we've seen is whenever your teammates or anyone in your company or you're a sole proprietor or whatever whenever you fly, process, and upload in that little cycle right there, it really closes the loop on understanding what did we do, when did we do it, hey, what did you fly a couple days ago? Just having that easy accessibility to have the raw data, the actual process data organized into that loop, and you can upload it right from Rack Desktop. I think that's been a kind of a game changer unlock to just organizing all these files. I mean, I remember whenever I had an M600 and a Regal system, I had it was just a Tupperware full of external hard drives, and I would sit there, and someone asked me for an old project data, and I go through these external hard drives just to find, oh, where did I have all that data? But now I organize it all in the Rock Cloud, and now I could be on my phone. Someone can ask me for a project or say, hey, can you check this out really quick? And it's super quick for me to communicate with our team uh, on these data sets or what they've been flying. So in the back end behind this whole presentation was the Rock team, Andrew and Jamie and Vicky and Garrett and the team just going out there capturing data sets, communicating with me and the rest of the team using our own tools. And so oftentimes we build new features that satisfy, just making things easier on life. And I think that's been a big thing about Rock Robotic is like how do we make 3D easier and not only that accurate, and then just keep improving on your capital investment over time. Because at the core of it, internal to these pieces of hardware, it's phenomenal quality, pieces of components in there. The IMU is super high end. You have a triple band GNSS receiver, and we have the Rock bases, and it's the same GNSS receiver inside of that. And these things are, I compare it to the Trimble systems, and I mean they do the same. And so it's each individual thing, and even the laser scanner that does a half a centimeter precision accuracy. So each shot that's emitted, it can measure up to a half a centimeter in accuracy. And then when you compound that with you're on a vibrating platform, twisting around in the sky and flying, and we're getting it down to that 2 centimeter, right around this range of accuracy. Like that's phenomenal, right? So Anyways, I just wanted to jump in here at the end and say thanks to Andrew and thanks to the Rock team for putting this whole thing together for everyone. I know you guys probably have enjoyed. Hope you learned a few things through this process today in this webinar. You can always reach us at sales@rockrobotic.com. We're available all the time. We're working on a few new things. We're encoding all of our knowledge into some of these AIs. So you're going to be able to always learn more by talking and getting our Rock team's collective expertise, at your fingertips at any moment, which is internally, we've been doing this as well. And it's really awesome. And then the Gaussian splat I showed you, if you want to pop that up one more time, because I just want to show it one more time, because I think it's just cool, guys. I just want to jump around and just zoom around this data set for a second. And this is actually mid-process, because we captured this recently and we were processing it last night. And so this isn't even totally done yet. And just being able to see the future of 3D. That's a picture right there, a picture of the background, and you can see all that. So the future is pretty awesome, guys. And here at Rock Robotic, we're committed to making products and services and software and helping you along the way, every step of it, to make sure you're successful whenever you work with us. So we hope you guys become customers of Rock. And I'm going to pass it back over to Andrew. You can stop. You want me to go to the what cuts?
Yeah, Harrison, I was going to say you really missed the opportunity to talk about the what's on tap and have a tap room in the picture.
Was that over there?
Well, I mean, that's a brewery tap room. So this is what's on tap coming from Rock. Never mind having to, instead of checking the list or some app, you can just bring this up and get your 3D visualization of the chalkboard that shows what's on tap. So
I totally agree. I really like looking at the ceiling, actually. That's the thing that really gets me going, like all that.
We're an odd bunch. You like ceilings, I like curbs and creek beds. Maybe we'll get someone a bit more who just wants to look at a landscape. So
all right, am I done zooming around?
I think you're done. As I will, shameless plug, Harrison did mention that the bundle includes the hardware, the software, and the processing. Also, shameless plug, as I said, it does include support. So when you have those questions about getting started with your unit, or there's something about processing that you're running into, or just want to bounce ideas off of about the best way to do a combined SLAM and airborne merge for a data set, that's where we come into play. And you can reach out to myself, the rest of the team. We all, as Harrison said, we get our hands dirty. We go out. I mean, like Harrison said, like he checks our data sets. He will send us back into the field if it's not the quality, and we'll learn the best way to do a data collection for merging SLAM and airborne, and then share that with you so you don't have to deal with the trials and tribulations.
Totally. All right, do we have any more questions? We can open it up for a couple more seconds. Is there any measurability with the splat? So technically, actually, it's very interesting. The splat is actually a point cloud, so all of our tooling works with it. But we're working on a few interesting things with the splat. So currently, yeah, we'll talk about it later. So short answer, yes. But there's a lot of cool things that since we've been in this 3D space for so long, building these tools that we can port over and instantly have a very awesome experience for third-party splats as well as Rock-made splats.
It's what's on tap.
It's what's on tap. All right. Well, if we don't have any more questions, thanks everyone for joining us today on this live stream. It will be on replay. You can see it again on our YouTube channel at Rock Robotic on YouTube. And I believe on LinkedIn, you can always go to our LinkedIn page. You'll see it again. But again, thank you. Thank you, Andrew. Thank you for the Rock team for putting this together. Let us know if you have any questions, and we'll always be here to answer them.
Thanks, everyone.
Have a great day.
Bye.
Thank you for joining us for today's event and being a part of this incredible journey. We here at Rock Robotic hope you're feeling inspired and ready to take the next step. Feel free to reach out to our team for any and all questions. We're here to help you decide what's the best fit and right for you. Together, We will rock on.